Hello everyone, Aaron here and welcome back to Leetcode. Today we're doing the minimum average difference problem. I'm on holiday at the moment, so this is a pre-recorded video, but hopefully I'll be back soon. So, you are given a zero-indexed integer array nums of length n. The average difference of the index I is the absolute difference between the average of the first I plus 1 elements of nums and the average of the last n minus I minus 1 elements. Both averages should be rounded down to the nearest integer. Return the index with the minimum average difference. If there are multiple such indices, return the smallest one. The absolute difference of two numbers is the absolute value of their difference. Fine. The average of n elements is the sum of n elements divided by integer division n. The average of 0 elements is considered to be 0. Okay. The average difference of index 0. So index 0, we take the 2 on one side. So the average of these is 2. We take the 5, 3, 9, 5, 3 on the other side. The averages of those is 10, 16, 25 divided by 5 is 5. So the difference between 2 and 5 is 3. And we do that, so then we can do it for 2 and 5. The average there is 7 integer division 2, which is 3, and 3, 9, 5, 3. Integer division 20 over 4 is 5. Difference is 2. The minimum average, the average difference of index 3 is the minimum average difference. Oh, so this one here, where we're at 3, the average difference is 0. 0, 1, 2, 3. So these 3, 2, 5, 3, and 9 have an integer average of 4. 5 and 3 have an integer average of 4. So the difference is 0. So the index you return is 3. Hey, that is confusing. Okay. So I'm just trying to think of the way to do this. So we can do this quite directly. For every I, compute the average of things up to I, compute the average of things after I, and calculate the absolute difference, and then find the minimum index such that that is true. But I think we can do a little bit better in the sense that the sums have a very obvious pattern to them. So, for example, self.nums is equal to nums, and self.sum is equal to sum of nums. So if we know these add to, what is that, 10, 19, 25, 27, if we're cutting here, we have a, actually no, well, yeah, so as we move our window along, the 2 gets moved from the sum into the tail. So this 27 drops by 2, and this trailing sum increases by 2. Same thing happens with the 5. This side grows to a 7. This side drops to a 20, and so on and so forth. So in fact, maybe I don't want those. So I do want the sum. The total is the sum of the numbers. In fact, let's name this slightly differently. Let's call this after and before. For I, v in enumerate nums, what we want to do is we want to do before gets incremented by v, and after gets decremented by v. So now we sort of know the sum before and after this integer. Excuse me. N is len nums. So the average before is going to be before integer division I plus 1, because for index 0 we've got one element and so on and so forth. And then the average after is going to be after integer division n minus I minus 1. So hang on, I forgot. 1, 2, 3, 4, 5, 6 elements. I is 0. So 6 minus 0 is 6. We want to lose one more. Yeah, so we do need this minus 1. So I was just staring at that, which is sort of, I wanted to confirm that that was the correct calculation. So now I have the averages before and after. I need the absolute difference. So then it's going to be min diff is going to be infinity. So the min index is going to be, well, let's say -1. It doesn't really matter. If diff, in fact, we can make it none, just for clarity. If diff is less than min diff, in fact, no. What I'm going to do is I am going to make this infinity as well, because it asks us to return the smallest integer, smallest index if there's a tie. If diff is less than min diff, if, in fact, no, we don't need to do that at all. What am I saying? Basically, we make sure this is an absolute check, a strict check, rather than an equality check, because we're seeing these things in order. If I had something that was equal to the minimum difference, well then I shouldn't update it, because I will have already found something with that difference. If diff is less than min diff is equal to diff, min index is equal to index. So I'm just going to turn that into 0. Oops. Return min index. We will always have some element. I'm just worried about this guy. This could be a divide by 0. I think I want to handle the case of length. Oh, hang on. No, this last one. If I is equal to n minus 1, average after is equal to 0, else. So there's this case at the very end. If we're looking at index 5, 0, 1, 2, 3, 4, 5, there's nothing after it, so we do need to handle that case separately. Is this sufficient? I think this might work. Let's give it a test. Built-in function index. Whoops. I. There we go. Let's use all the example test cases. Can I have an empty... No, I can't have an empty list, so I don't need to bother trying to test that. So let's see if it works for these. It does. Excellent. Now the question will be, is it fast enough? The complexity of this is this takes order n time. This is order 1 in Python. This whole loop, everything in here is order 1. So this is order n time. So this is an order n algorithm. I don't really know if we could do a lot better, because we're not given any guarantees about the shape of the list. let's click submit. So just on that comment I just made, oh, we got it right, perfect. I said we don't know anything about the shape of the list to do any better. So the comment I'm making there is about the big O complexity. So I've said this is order n. Obviously, you can process lists faster than order n if you're doing something that doesn't require you to look at every element. So if you're doing a binary search, for example, you can deal with a length n list in log n time, because if you go to the middle and you can eliminate half the list, you don't need to even look at that half of the list. But that requires you knowing that the list is sorted. That's something you know about the shape of the list. We don't know anything about the shape of the list, so it's very hard to say we could do any quicker. And we didn't need to do any quicker. We're very middle of the pack by the look of it. This is the solution, I imagine. So yeah, I'm not too upset with this. It's fairly tidy. Would I do anything differently? Honestly, probably not. I don't mind this. I may not have factored out n. That's just a tiny thing in Python to make it go a little bit quicker. Because Python is absurdly dynamic. There is a small cost to calculating the length of the list here every time. It's small and it's constant, but it's there. Whereas if it's just a variable, it's much, much faster. It's a local variable lookup. Anyway, that is entirely details that we don't need to worry about. So that is going to be it from me. I do hope you're having a wonderful break if you're on break. If not, good luck working through this period. Happy holidays, and I will see you next time. Bye.